Hello everybody, welcome to, I guess, astronomy class. This is what it's going to be like for the next couple of weeks. I'm going to go through the PowerPoints just like I would in class. I'm not requiring you to copy the notes anymore because that was what you're supposed to do in class and we're not in class, so now I just have to take your word for it that you're doing that. The drawings should be posted by the time this video is posted, so you got that to do. So pretty much all you guys got to do is watch this, read the book, and do your drawings, and then there's another assignment that I'll attach at the end. Since there's not going to be the same type of class time, we might be the test questions might be a little harder, right? Because they can't do multiple choice, because then you guys can just look at the answers when you're doing them. So as far as the test and everything goes, you're going to really want to know the chapter well. You're going to want to know how to explain things. So after I do this, I would encourage you guys to, even though it's not listed anywhere as homework, I would encourage you to read the section. So this is chapter 11, inferring stars. Inferring patterns in star life cycles. So if you'll remember from chapter 10, we learned specifically, or the biggest thing in chapter 10 was that HR diagram, right? That mapped the spectral type and the surface temperature compared to the luminosity and the absolute magnitude. And we looked at, the hot stars are blue, the cool stars are red. We know that the closer they are, the brighter they are usually. We know there's all those fancy relationships. Some stars have different spectral lines than others. We know brown dwarfs are things that almost became stars, but not quite. We know red dwarfs are stars, but they barely, because they only glow with red light. They're still technically stars, though. And we know that the more massive a star is, the higher up and on the left to the HR diagram it would be, which means the larger mass, the bluer the star, essentially. So we're kind of still, all that stuff, as I said, we cannot forget any of that going further in this book. As I said before, the farther we get in now, the chapters depend on you remembering everything we've learned. And it's not just a review, like what Mars is or what Jupiter is, it's actually new information. So let's go ahead and get started. When looking into the night sky, one naturally wonders if the stars overhead are the same stars that dotted the skies of our grandparents and that of our great-grandparents. Indeed, the stars that illuminate our night seem eternal and unchanging. But this permanence is an illusion. Each of the stars visible to the naked eye shines due to thermonuclear reactions and has only a finite amount of fuel available for those reactions. What that means is that stars cannot last forever. They form from material in interstellar space, evolve over millions or billions of years, and eventually die. In this chapter, our concern is with how stars form and change over their life cycles. A couple other things that you guys kind of snapshot into what we might be talking about. Many stars are made up of the remnants of older stars, which might be news to you. Some stars are created from the remnants of older ones. Some of them are still burning from the beginning, and whether you think the beginning was a couple thousand years ago or a couple billion years ago, it doesn't matter. Some of the stars have been burning since the beginning. Some of them have burnt out. As we will see, stars mature and grow old, and their rate of aging is directly related to their mass. In this chapter, we will focus on what happens to the most common of stars, like our own sun. So 11.1 says, stars form from the gravitational collapse of immense clouds of interstellar gas and dust. Remember, interstellar means it's like in between the stars. So there's just a bunch of dust and gas out there floating around, and if it's thick enough, eventually it just kind of collapses in on itself and becomes a star. Star lifetimes exceed human lifespans, so they must be studied by looking at numerous stars at different stages in their life cycle. It's impossible for us to look at a star right now and watch it until it dies. Stars live for so much longer than we do that it doesn't make any sense for us to watch one star from birth to death. Instead, what we have to do is look at all the stars out there and say, okay, well, that one just exploded. That one looks like it just started. This one looks similar to that one, which is around some other stars that are exploding, so maybe it's going to be old soon. So we pretty much have to just piece together what we think might happen, because even the span of human history is a fraction of a star's life cycle. So we can't really watch one. We just have to put it together. So a star like the Sun has enough usable fuel in it to last for about 10 billion years. So based off of all of our math, we would assume that a star like our Sun can burn for 10 billion years. That's ridiculously long compared to even human existence. So we can only know what we have at this snapshot of time that we're even alive. In between all of these stars, though, there's a bunch of gas, and gas and dust makes up what we call the interstellar medium. So whatever a medium is, it's the stuff like between stuff, right? So if we were in person and I'm talking to you, the sound waves are going through the medium of air. Or if you're in a pool swimming, then you're swimming through the medium of water. In between space, there's interstellar medium. It's just gas and dust and a lot of nothing, to be honest. There's a lot of space in between each of these things. But where they are clumped up, we get things called nebula. And we have talked about nebula before. We've talked about different types of nebula. First one, our emission nebula. And these would kind of be the... let's do this. So the emission nebula are the ones that we would be talking about that give off light, right? Emission means they're giving off light. So they are glowing, and they are ionized because the stars nearby are hitting this gas with so much energy that the gas itself gets excited and starts lighting up and shooting out a bunch of colors in different directions. Here's an example which, since we don't have a projector, I actually think this ends up looking better because it's a higher quality picture than the projector can even put into place. What this actually is, if you guys know what the Orion Nebula is, let's look that up real quick. Oh, not a nebula. Oh my gosh. Constellation. It's this guy. You might have seen he's like a little hunter. This is actually one of the quote-unquote stars in there. So one of the stars looks red and hazy, but if we zoom in, it actually isn't even a star at all. It's this gigantic cloud of dust that has stars in it. And to give you an example of how big these, like, that's a star, right? So if you can pretend like that's the sun, that's how big this cloud is, that stars are just dotted inside of the dust. That's how big this cloud is. So the scope of this entire cloud is staggering, and the fact that stars exist inside of the cloud and the cloud is this big. Here's a picture from your book that kind of shows you different spots. We have a little dark bay, which means there's like some dust going in front of some stars behind it. We have like little shock waves of new stars forming. And when the new stars form, they kind of like shoot little shock waves, so we can see that there. We have the endpoint of major outflow, so like we can see there's all sorts of different terrain features, almost, if you will, of this cloud based off of the stars inside of it. So that's an emission nebula, and a lot of it looks kind of pink and reddish because remember, when you heat up helium and hydrogen, they kind of, especially hydrogen, they kind of give off that pink light. So it makes sense that these stars are giving off enough energy to light up, to make this gas light up and emit its own light. Okay, it's not a reflection. This light is energizing this dust and making that dust give off light. There's also things called dark nebulas. Dark nebulas are so dense that they are opaque. Opaque meaning you can't really see through them. And they appear as dark blots against the background of distant stars. So if you ever look up through a telescope, and there's this black splotch. That's probably a dark nebula, which means all these stars exist, and this dust is probably in between us, right? So like, let's say you're Earth, and I'm a bunch of stars. The nebula, the dark nebula, would be like my hand, preventing you from seeing me. Does that make sense? The few stars you see here are actually between the nebula and you right now. So it's not like these are poking through the cloud, these are in front of the cloud. Something interesting about these nebulas. So the ones that we were talking about, the emission nebulas, the one that we're giving off light, that has about a few thousand hydrogen atoms per cubic centimeter. Okay, so if we have this little thing, a centimeter is almost as big as a little circle in there. So pretend in that circle there's a couple thousand hydrogen atoms. In contrast, the air that we're breathing right now has 10 to the 19th atoms in that same space. So that's the difference. The air that you're breathing is that many times thicker than these nebulas are. But the nebulas are so massive that they make these gigantic pictures. Dark nebula, the ones that we saw in this picture, have 10 to the 4th to 10 to the 9th particles, which means they are still way less dense than the air you're breathing. The air you're breathing has way more particles than this dark nebula does. The only thing is that the clouds of these dark nebulas are so massive that they can end up blocking out the light behind it, because this thing is takes up so much space out there. It's crazy to think about. Reflection nebula then can you guess what they do? They just reflect light. They're getting hit with light. They're not getting so energized that they create their own light, but they are reflecting the light from the sun. So here we see a blue star hitting some gas. This gas is not emitting its own light. It's simply reflecting the blue light from here. Does that make sense? So we got emission nebula, which are giving off their own light, like this. The stars heat up the gas so much that the gas gives off its own light. We have dark nebulas that block out stuff behind it. And we have reflection nebulas, which are blue in this case because they were just reflecting the blue light. So this question is saying, what would a reflection nebula become if it could be compressed to 3 times its typical density? So if we had a reflection nebula and compressed it, probably become a dark nebula, because these nebulas all have pretty much the same composition, and that is mostly hydrogen with a little bit of helium and barely some other stuff. So it's just saying if it was reflecting, but you made it a little more dense, what would happen? It would probably just become a dark nebula. So out in these gigantic dense clouds out there, eventually gravitational attraction can cause some of these materials to condense into what we call a protostar. This is not in every single nebula out there. It's probably only in dark nebulas because those were the most dense that we just talked about. This is a really cool picture of something. So in the darkest clouds, eventually there's enough material to kind of form its own gravitational pull. And as we were talking about previously, if you get enough material to start squeezing in on itself, what happens is the squeezing itself starts to heat up all the materials, right? So as the protostar collapses, gravitational energy is converted into thermal energy, which makes the gases heat up. And that can cause actually quite a bit of light. So what you're seeing right now is a protostar doing exactly what we talked about. So in May 2002, we were able to pick it up. And you see all this like circle around it? It let out a pulse of light, and this part of the gas is being lit up with that. Okay? So what this is not, it's not a picture of the gas moving outward. What this is it let out a burst of light, and in May, this is what the light was able to show us. In September, this is what the light was able to show us. In October, it showed us this, and in December, it showed up this. That's how massive this gas cloud is, that it's taking light this long to travel to show us what this nebula, how large this nebula is. Okay? This is not a movie of the gas expanding. This is a picture by picture what the light pulse is lighting up for us to see. That's how large this is. It took months for light to leave this star and light up all of this stuff. And it gives us this awesome picture. Like, look at this stuff. This is crazy. So here we see T-Tauri stars, are protostars with emission lines as well as absorption lines in their spectra, whose luminosity can change irregularly as they eject material into space. So when stars are kind of forming, protostars, these T-Tauri stars are both emitting light and absorbing light. It's this weird kind of concept that's happening that we'll see the reason why in a couple slides. But they are both emitting light and absorbing light at the same time. The dusty material being added to the protostar is known as a circumstellar accretion disk. Circumstellar means around the star, accretion meaning it's gaining, and disk meaning in the shape of a disk. And the surrounding materials that form planets are called protoplanetary disks, or proplyds. So we've seen these pictures before, and I want to say chapter, I don't know, in the beginning of the year, in the earlier chapters. So T-Tauri stars have masses less than about 3 times larger than the mass of our Sun. The emission lines show that these protostars are surrounded by a thin, hot gas, and the Doppler shifts of these lines suggest that the stars are ejecting gas at 180,000 miles an hour. They are able to slowly add mass to themselves at the same time that they rapidly eject material into space. Because the material is spinning around it, sometimes the materials get hit, they slow down, and then they end up getting sucked into it instead of being shot out like that. We know that the material spinning around it will either end up in the star, be ejected away, or end up in little chunks that we call planets. Going back to here, we see a star over the course of a couple years ejecting a bunch of hot gas. So this is 500 light years away, has been expanding over the past 30 years. This star is ejecting a bunch of stuff. This is 200 astronomical units, which means if we go from the Earth to the Sun and do that 200 times, that's how wide this is. So this is a very large area, and we can see over over 5 years, all this stuff expanding, and I'm sure if we took a picture now, it'd be even more spread out. Here we see 200 astronomical units again, so this is an even farther zoomed out picture of something else, of another protostar essentially forming. It's shooting out stuff. We see that it's pretty much glowing the same. Here it seems like the right side is a little bit giving off a little bit more light than this is. Right? This is a little brighter than that. These protostars can mature into stable main sequence stars quickly. The speed at which they do so depends entirely on their starting mass. An HR diagram of protostars shows that a protostar at 15 times the mass of our Sun becomes a star in about 100,000 years, while a much smaller protostar, like the one that is about the same mass as our Sun, would take more than 10 million years to form. So this question says, do protostars increasing in brightness gain mass or reject mass during formation? Kind of a trick question. Remember, they do both. So through dust-grain collisions that slow the material, causing mass to migrate into the protostar, and simultaneously they lose mass through a T-Tauri wind process during formation. So it's spinning around, right? It's spinning around, getting sucked into the middle, but also it's shooting off a bunch of mass thanks to the T-Tauri winds during their formation. So the answer to this is it does both. Stars do both. We will learn in chapter 14 that a star-filled galaxy's moving spiral arms can cause clouds to compress and initiate star birth. But this is not the only way stars can form. Presumably, anything that compresses interstellar clouds will do the job. So one way that we can compress, one way that clouds can be compressed is by a supernova. As we will see in Chapter 12, the core of the doomed star collapses suddenly, which releases vast quantities and particles and energy that blow the star apart. The outer layers are blasted into space at the speed of several thousand kilometers per second. And this stuff gets thrown out as a bunch of remnants. Excuse me, I'm sorry. Here we see how long it takes for a star to form, becoming a main sequence star. Okay? So if you follow this line, it takes about 10 to the 4th years, which is a pretty big, 10 to the 4th years to go from here to enter the main sequence. However, a 1 solar mass protostar, like our star, takes 10 to the 7th years, right? So 15 times larger than our sun, it takes 10 to the 5th years. 1 times the mass of our sun, it takes 10 to the 7th year. This takes a lot longer to enter like this main sequence than these big stars do. What that pretty much comes down to is that the bigger stars enter the main sequence before smaller stars do. Here is a composite picture of what a supernova looks like. This is a combination of infrared, visual, and X-ray images all mapped together. This picture is about 10,000 light years away, and it's 10 light years wide, which is insane. 10 light years wide. Any red you see is the infrared, any of the yellow is the visible light, and the greenish and bluish is all the X-rays. So if you put all that stuff together, we get this awesome picture. The only reason why we can see this stuff is because thanks to the explosion of the supernova, all these gases are heated up at different images, and some of it's giving off invisible light, some of it's infrared, and some of it is X-ray. So what happens is this star explodes. As it explodes, there's a shock wave that goes out, and it compresses this gas. Okay, so it was thin. We smush the gas, and once we smush the gas, we get into that pattern that we just said. The gas gets compressed. As it gets compressed, it starts to gain more and more mass. It starts to heat up, and eventually it becomes a very poor resolution photograph over here, but eventually it becomes a star. So the question is, what physical process is needed to initiate the formation of a star? Any type of compressive physical process. So whether that be a supernova exploding and shooting a big old shockwave to compress a bunch of gas and make more stars, or, as the book kind of hinted at, maybe the galaxy itself is kind of throwing around gas clouds, and maybe the gas clouds can smack into each other and make stars. And that's it for 11.1. So if I were you, I'd go ahead and stop, maybe do a couple drawings before watching the next video.